Welcome everyone to this lecture on evaluating performance, particularly for classification problems. In the next lecture, we'll discuss evaluating performance for regression tests. So we just learned that after our machine learning process is complete, we're going to be using performance metrics to evaluate how our model actually did. And we keep mentioning the fact that we train our model on the training data, and then we're going to use some sort of metric to actually see how it performed on either the test set or the validation set. So let's go ahead and discuss what that actually means. What classification metrics are we going to be using? And the key classification metrics we should be understanding are accuracy, recall, precision, and F1 score. But first, we should understand the reasoning behind these metrics and how they will actually work in the real world. Typically, in any classification task, your model can actually really only achieve two results. Either your model was correct in its prediction, or your model was incorrect in its prediction. And all classification metrics stem from this idea. Now, fortunately, incorrect versus correct also expands to situations where you have multiple classes, such as trying to predict categories of more than two. For example, you have category A, B, C, D. You can either be correct in predicting the correct category or incorrect in predicting the right category. Now, for the purpose of explaining the metrics, we're going to go ahead and simplify this to what's known as a binary classification situation. Binary meaning two. So there's only two available classes, either class 0 or class 1. And this idea is going to expand to multiple classes as well. But for simplification, let's imagine just a binary classification situation. So in our example, we're going to attempt to predict if an image is a dog or a cat. And we'll actually perform this task later on during the convolutional neural network portion of this course. Now, since this is a supervised learning problem, what we're going to need to do first is fit or train a model on training data. That means we're going to have images that someone's already gone ahead and labeled dog or cat, so we know the correct answer on these images. Then, we're going to test that model on the testing data. So we're going to show new images that the model hasn't seen before, get the model's prediction, and then compare the results of the model prediction to the correct answer that we already know. So once we have the model's predictions from X test data, we compare it to the true Y values, the correct labels. So let's actually diagram this process out. Let's imagine we've already trained our model on some training data, and now it's time to actually evaluate the model's performance. This is where our test data set comes in. So we take a test image from what we're going to label X test. X meaning features. So the actual image itself is a feature, and this is from the test set. And there is a corresponding correct label from Y test. So we have the feature or image X, and that's a test image, and we also have the correct label from Y test. And in this case, we can see that this image is an image of a dog. So what we're going to do is we're just going to feed in the features, in this case the image, into our already trained model. And then the model is going to make some prediction. So the model predicts that this is a dog. And then what we do is we compare the prediction to the correct label. So does dog equal dog? And in this case, it was correct. However, maybe it predicted that this image was a cat. And in this case, this comparison to the correct label would be incorrect. And these are essentially just the only two situations. Either you're right or you're wrong, correct or incorrect. So we'll repeat this process for all the images in our X test data. And at the end, we will have a count of correct matches and a count of incorrect matches. And the key realization here that we need to make is that in the real world, not all incorrect or correct matches hold equal value. So let's kind of hone in on what we mean by that. So in the real world, a single metric won't tell the complete story. And to understand all of this, let's bring back those four metrics we mentioned and see how they're actually calculated. We could organize our predicted values compared to the real values in what is known as a confusion matrix. So we'll touch upon the confusion matrix later on, but first let's talk about accuracy. Accuracy is one of the most common classification metrics, and luckily it's also the easiest to understand. It's just really intuitive what it's measuring. Accuracy in classification problems is the number of correct predictions made by the model divided by the number of, or the total number of predictions. So again, it's the number of correct predictions divided by the total number of predictions. Essentially answering the questions, how many predictions did you get right as a percentage? So for example, let's imagine that X test set was 100 images, and our model correctly predicted 80 images. Then we have 80 divided by 100, or 0.8 or 80% accuracy. And accuracy is really useful when the target classes are well balanced. So what does that mean, well balanced? Well, in our example, that would mean we have roughly the same amount of cat images as we have dog images throughout our data. So it means the actual labels themselves are roughly equally represented in the data set. But let's imagine that we have what's known as an unbalanced class situation. In this case, accuracy is actually not a good metric to use. So let's do a little thought experiment. Let's imagine that in this test set, we had 99 images of dogs and only one image of a cat. Now, if our model was simply a line that just always predicted dog no matter what image it saw, then we would actually get 99% accuracy on this particular test set, because by just always saying dog, 99 images are dogs and one image is of a cat, then we only missed one. So that's why you have to be aware of the downside of accuracy. And the downside really comes when you have an unbalanced class situation. If your classes are roughly balanced, then accuracy is a very nice intuitive method or a metric to understand. However, if you have an unbalanced class, you can see in this particular situation where it starts to represent a problem. And that's where the other metrics come into play. So again, in this situation, we'll want to understand recall and precision. That helps us understand how well it's performing on unbalanced classes. Recall is the ability of a model to find all the relevant cases within a dataset. And the precise definition of recall is the number of what's known as true positives, and we'll kind of hone in on that later when we see the confusion matrix, but it's the number of true positives divided by the number of true positives plus the number of false negatives. And the precision is the ability of a classification model to identify only the relevant data points, where precision is defined as the number of true positives divided by the number of true positives plus the number of false positives. Now, often you have a trade-off between recall and precision. While recall expresses the ability to find all the relevant instances in a dataset, precision expresses the proportion of the data points our model says was relevant that actually were relevant. And then F1 score is essentially a combination of these two. In cases where we want to find an optimal blend of precision and recall, we can combine the two metrics using what is known as the F1 score. And the F1 score is the harmonic mean of precision and recall, taking both metrics into account in the following equation. So this isn't just taking the average of recall and precision, it's taking the harmonic mean of them. And so here we have the formula for F1 score, where F1 score is equal to 2 times precision times recall in the numerator, and then divided by precision plus recall in the denominator. So the reason we use the harmonic mean instead of just a simple mean or simple average is because it's going to punish extreme values. For example, if you created a classifier that had a precision of 1, meaning essentially perfect precision, and a recall of 0, essentially the worst recall possible, if you were just to take the simple average of this, then it would be 0.5. But the F1 score, because it's taking a harmonic mean, we have precision times recall there at the top, which means you get 0 times 1 at the top, and you get an F1 score of 0. So this is really nice because it lets you punish extreme differences between the precision and recall. So it gives you kind of a fairer assessment of that trade-off between precision and recall. Now we can also view all correct classified versus incorrectly classified images in the form of a confusion matrix. So confusion matrix looks something like this. We have the underlying true condition, so that's the true correct label, and we can think of condition as positive or negative, such as actually being a dog or not being a dog, or oftentimes this is used in a medical diagnosis, such as having presence of a disease versus not having presence of a disease. And then we have the model's predicted condition, so prediction positive or prediction negative. And I think when it comes to confusion matrices, it's often easiest to first get an intuition if you think of this as a diagnostic test for having some sort of disease present in a person after maybe you take a blood sample and run it through your model. So for example, a true positive would be someone actually having that disease and your model correctly predicting that they have it. A true negative would be someone not having the disease and your model predicting correctly that they do not have the disease. So you have true positives and true negatives, and those are both correct predictions. And then we have essentially these two types of incorrect predictions, a false positive and a false negative. A false positive would be if the person doesn't have the disease and you predict that they do have it. That's a false positive because you are falsely saying that they are positive for this disease or this condition. A false negative is essentially the opposite of that, where this person does have the disease present, and then you report back using your model and your test that it's actually negative. They don't actually have this disease. And these are also sometimes called in statistics a type 1 error and a type 2 error. And then off of these essentially true positive, true negatives, and false positives results, there's a lot of other metrics you can calculate. So we can see some of them here, such as on the bottom left corner, we can see the actual calculation for accuracy. It's the sum of true positives plus true negatives, essentially the sum of what you got correct over the total population. And then there's a bunch of other ones like positive likelihood ratio, false positive rate, true positive rate, prevalence, false discovery rate, etc. Now the main point to remember here is that the confusion matrix and the various calculated metrics is essentially they're all fundamentally ways of comparing the predicted value versus the true values. And what constitutes good metrics actually really depends on the specific situation. A really common question I get from students is, hey, is this a good enough accuracy? Well, that really depends on your situation and the context of the situation. Now, if you're still confused in the confusion matrix, it's no problem. Check out the Wikipedia page for it. It has a really good diagram with all the formulas for all the metrics. And throughout the training, in this course, we're usually just going to print out metrics, such as printing out basic accuracy. Now, before we finish off this lecture, I want to go back to that initial question I mentioned that students ask me all the time, which is this idea of what is a good enough accuracy? And as always, this really depends on the context of the situation you're running your model in. There's no single number I can give to say something like 90% accuracy is good enough for every situation. We already saw the issue with unbalanced classes, but there's also not really a good remark I can give for what is a good enough precision or recall. And we have to think of the context of the situation. So let's think back on maybe that model that is diagnostic for predicting the presence of a disease. So if we created a model to predict the presence of a disease, first thing I want to think about is, are we going to have balanced classes or unbalanced classes? So is the disease presence well balanced in the general population? And in pretty much most cases, it's probably not. There's probably not a disease that's going to happen where about half the population is affected and half the population is not affected. So we can already tell we're going to have an unbalanced class situation, which means we're going to have a precision recall trade-off. So we should also keep in mind that often these models are used as quick diagnostic tests to have before having a more invasive test. For example, for prostate cancer models, it's really common to just do a simple urine test before getting a biopsy because it's much easier to just get your urine tested than going through a full biopsy on the prostate. So we also need to consider then what is at stake. If it's prostate cancer, the stakes are actually quite high. So as we mentioned, we often have that precision recall trade-off, which means we essentially need to decide if the model should focus on fixing false positives versus false negatives. So at the cost of decreasing false negatives, most likely we increase false positives and vice versa. And in disease diagnosis, it's probably better to try to minimize the number of false negatives at the cost of increasing the number of false positives. So we go in the direction of these false positives. And why do we actually want to do that? Well, we want to make sure we correctly classify as many cases of the disease as possible. So at the cost of increasing false positives, we try our best to decrease false negatives in this context of disease diagnosis. And why would we actually want to do that? Well, we want to make sure that anyone that actually has some sort of presence of this disease, or in this case of this example, prostate cancer, if we're doing that urine test, we want to make sure that all those people that have the presence of the disease will actually go through to the next step that is maybe a more invasive test like a biopsy. And remember, this kind of usually comes at a cost of increasing those false positives. So our models aren't going to be perfect, and eventually what's going to happen is someone who doesn't have the disease, when we do our simple urine test or whatever our machine learning model is, it's going to predict back that, hey, I'm sorry, but you have the positive presence of this disease. And it will be an error because it will be a false positive. However, then when they get the more invasive tests, then they'll realize, oh, sorry, it was a false positive. You're actually okay. You don't have this disease. And that comes because we're trying to minimize the false negatives. What we really don't want when it comes as something as important as having cancer, having a disease, we really don't want to turn someone away who actually has the disease and tell them they don't have the disease. So that would be a false negative. When it comes to disease diagnosis, that's something we really want to minimize. We want to minimize those false negatives so we don't accidentally miss someone right off the bat with our diagnostic tool and tell them, oh, you don't have the disease or you don't have cancer, when they actually do have it. So we can see for something as important as disease diagnosis, really minimizing those false negatives becomes really important. And pretty much all of this is to say, machine learning is not going to be performed in a vacuum. And these performance metrics don't have some sort of universal truth that is true across all problems. But machine learning is instead, it's a really collaborative process where we should always be consulting with experts in the domain. For example, in this case of disease diagnosis, we should probably be talking to medical doctors as far as what are acceptable standards for false negatives versus false positives, what is the general presence of this disease in the general population, etc. And this is going to change depending on the context of your situation. So always keep that in mind. There's not going to be an easy answer for me to say, is this a good enough accuracy, precision, or recall? Because it all depends on the context and the domain of the situation. Okay, so we just talked about how we can evaluate classification models. Let's go ahead and move on to the next lecture where we discuss evaluating regression tasks. I'll see you there.